Hello everyone and welcome back to another video. And today I am going to talk about Generative Adversarial Network. If you want to download the source code, then check the link in description. Now before jumping to code, let me explain some of the basics first. GANs are a class of unsupervised learning algorithms that do much more than just recognizing image/voice, predicting or translating. They implement deep neural networks or CNN and are comprised of two parts, pitting one against the other, thus the adversarial. These two parts are called the generator and the discriminator. Generator. The generator takes the role of a forger and tries to create music/image/speech from random noise. It learns to map from a latent space to a particular data distribution of interest. It generally implements a deconvolutional network to do so. Discriminator. The discriminator, on the other hand, takes the role of the evaluator and tries to distinguish the fake data, created by the generator, from the real one. It is usually implemented as a convolutional network. With that said, what follows is a loop in which the generator tries to maximize the probability of fooling the discriminator by making the images, for example, more close to real in each step, thereby making the discriminator classify them as real. And the discriminator guides the generator to produce more realistic images by classifying its images as fake. Let's fit this into an analogy. You can think of a GN as a game of cat and mouse between a counterfeiter, generator, and a cop, discriminator. The counterfeiter is learning to create fake money, and the cop is learning to detect the fake money. Both of them are learning and improving. The counterfeiter is constantly learning to create better fakes, and the cop is constantly getting better at detecting them. Competition in this game drives both teams to improve their methods until the counterfeits are indistinguishable from the genuine or real money. GANs have incredible potential because they can learn to imitate any distribution of data. That is, GANs can learn to create worlds spookily similar to our own in any domain: images, music, speech. In this kernel, I'm implementing deep convolutional GN, based on this paper on DCGN, which is in contrast to but builds on Ian Goodfellow's paper. Goodfellow's paper is the first paper on GN and implements a dense network both in the generator and the discriminator rather than a CNN. I am using the images, without class labels, from the Safar_10 dataset. These images along with the fake ones will be fed in batches to the discriminator. Let's take a look at the steps our GN will follow. 1. The generator takes in random numbers and returns an image. 2. This generated image is fed into the discriminator alongside a stream of images taken from the actual dataset. 3. The discriminator takes in both real and fake images and returns probabilities, a number between 0 and 1, with 1 representing a prediction of authenticity and 0 representing fake. Now let's start coding. We are going to start with importing all of the libraries. This code imports several modules from the Keras library and other standard libraries, defines a deep learning model, and prints the list of files in the specified directory. First, it imports the following modules from Keras. Input, a class for defining an input layer for a Keras model. Dense, a class for defining a fully connected layer for a Keras model. Reshape, a class for reshaping the input or output of a Keras layer. Flatten, a class for flattening the input or output of a Keras layer. Dropout, a class for applying dropout regularization to a Keras layer. Batch normalization, a class for applying batch normalization to a Keras layer. Activation, a class for specifying the activation function of a Keras layer. Zero padding 2D, a class for adding zero padding to a 2D input. Leaky ReLU, a class for specifying a leaky ReLU activation function. Upsampling 2D, a class for upsampling a 2D input. CONV2D, a class for defining a 2D convolutional layer for a Keras model. Sequential, a class for defining a linear stack of layers for a Keras model. Model, a class for defining a more complex Keras model with multiple inputs and outputs. Atom, an optimizer class for training a Keras model using the atom optimization algorithm. SGD, an optimizer class for training a Keras model using the stochastic gradient descent, SGED, optimization algorithm. Next, the code defines a deep learning model using Keras. The model architecture is not provided in the code, so we can't comment on its specifics. However, it likely includes several convolutional layers followed by fully connected layers, with activation functions and dropout regularization applied at appropriate points. Finally, the code prints the list of files in the /input directory. This is a relative path, so the actual directory may differ depending on the location of the script or notebook running this code. This code first imports necessary functions from the OS and os.path modules, which allow for manipulating the file system. Specifically, the functions being imported are lister, makers, join, exists, and expand user. The code then sets the cache_dir variable to the path /.keras, which is the default cache directory used by Keras, a deep learning framework. If this directory does not exist, it is created using the makers function. Next, the datasets_dir variable is set to the path /.keras/datasets, which is a subdirectory of the cache directory. If this directory does not exist, it is created using the makers function. Afterwards, the code copies a file called safar10python.tar.gz from a directory called /input to the datasets directory using the cp command. It then creates a symbolic link from this file to a file called safar10batchespy.tar.gz using the ln command. Finally, it extracts the contents of the safar10python.tar.gz file into the datasets directory using the tar command. This code appears to be setting up a directory structure and copying some data files into it, likely in preparation for training a neural network on the Safar10 dataset, a common image classification benchmark dataset. This code loads the Safar10 dataset using the Keras deep learning framework's built-in load_data function. The dataset consists of 50,032 by 32 color images in 10 classes, with 5,000 images per class. The images are divided into two sets, a training set and a test set. The training set is used to train a machine learning model, while the test set is used to evaluate its performance. Next, the code selects a single class of images, specifically the images in the birds class. This is done by indexing the x_train array with a Boolean array that has the same shape as the y_train array, where the value is true if the corresponding element in y_train is equal to 2, the class index for birds, and false otherwise. This filters out all images in the other classes and only leaves the images in the birds class. The resulting x_train array will contain only the images of birds from the Safar10 dataset. This can be useful for training a machine learning model that specializes in classifying bird images. This code defines some variables for use in a deep learning model. The variables img_rows and img_calls are both set to 32, which corresponds to the height and width of the input images that will be fed into the model. The variable channels is set to 3, which corresponds to the number of color channels in the images, red, green, and blue. The variable img_shape is then defined as a tuple containing the values of img_rows, img_calls, and channels. This tuple represents the shape of the input images that will be fed into the model. Finally, the variable latent_dim is defined and set to 100. This variable represents the dimensionality of the latent space of the model. The latent space is an intermediate representation of the input images that the model uses to generate new images. Increasing the value of latent_dim can allow the model to generate more complex and diverse images, but it can also increase the computational complexity of the model. The generator. To learn a generator distribution P, G over data X, the generator builds a mapping function from a prior noise distribution P, Z, Z, to data space as G, Z. The discriminator outputs a single scalar representing the probability that X came from training data rather than P, G. G and D are both trained simultaneously. We adjust parameters for G to minimize log 1D, G, Z, and adjust parameters for D to minimize log D, X, as if they are following the two-player min-max game with value function B, G winking and laughing. In the generator we use a method called upsampling to produce images. I have used upsampling 2D, but transpose CONV 2D plus stride or pixel shuffle could be used alternatively. This code defines a function called build_generator that creates a generator model for a deep learning application. The generator model is used to create new images that are similar to the images in a given dataset. The generator model is built using the Keras sequential API, which allows for creating a model layer by layer. The generator model takes as input a vector of random noise with shape, latent_dim, and outputs an image with shape, img_rows, img_calls, channels. The model first adds a dense layer with 128 by 8 by 8 neurons, which corresponds to a fully connected layer with 8 times 8 times 128 is equal to 8,192 outputs. This layer takes the random noise vector as input and applies a rectified linear unit, ReLU, activation function to it. Next, a reshaped layer is added to reshape the output of the dense layer into a 3D tensor with shape 8, 8, 128. This tensor represents an 8 by 8 grid of 128 dimensional feature maps. Then, an upsampling 2D layer is added to double the spatial dimensions of the feature maps, resulting in a 16 by 16 grid of 128 dimensional feature maps. A CONV 2D layer is then added with 128 filters and a kernel size of 3 by 3. This layer applies a convolution operation to the feature maps and uses a rectified linear unit, ReLU, activation function. A batch normalization layer is added to normalize the activations of the previous layer. Another upsampling 2D layer is added to double the spatial dimensions of the feature maps, resulting in a 32 by 32 grid of 128 dimensional feature maps. Another CONV 2D layer is added with 64 filters and a kernel size of 3 by 3. This layer applies another convolution operation to the feature maps and uses a rectified linear unit, ReLU, activation function. Another batch normalization layer is added to normalize the activations of the previous layer. Finally, a CONV 2D layer is added with channels, filters, and a kernel size of 3 by 3. This layer applies a convolution operation to the feature maps and uses a hyperbolic tangent, tan, activation function. The output of this layer is an image with shape, img_rows, img_calls, channels, which represents the generated image. The function returns a Keras model object that takes as input the random noise vector and outputs the generated image. Overall, this code defines the architecture of the generator model and returns it as a Keras model object that can be compiled and trained on a dataset. The discriminator. The discriminator is also a CNN with leaky ReLU activations. Many activation functions will work fine with this basic GAN architecture. However, leaky ReLUs are very popular because they help the gradients flow easier through the architecture. A regular ReLU function works by truncating negative values to 0. This has the effect of blocking the gradients to flow through the network. Instead of the function being 0, leaky ReLUs allow a small negative value to pass through. That is, the function computes the greatest value between the features and a small factor. Leaky ReLUs represent an attempt to solve the dying ReLU problem. This situation occurs when the neurons get stuck in a state in which ReLU units always output zeros for all inputs. For these cases, the gradients are completely shut to flow back through the network. This code defines a function called build_discriminator that creates a discriminator model for a deep learning application. The discriminator model is used to distinguish between real images from a given dataset and fake images generated by a generator model. The discriminator model is also built using the Keras sequential API, but it takes as input an image with shape, img_rows, img_calls, channels, instead of a vector of random noise. The model first adds a CONV 2D layer with 32 filters, a kernel size of 3 by 3, and a stride of 2. This layer applies a convolution operation to the input image and uses a leaky rectified linear unit, leaky ReLU, activation function with a slope of 0.2. A dropout layer is added to regularize the activations of the previous layer and prevent overfitting. Another CONV 2D layer is added with 64 filters, a kernel size of 3 by 3, and a stride of 2. This layer applies another convolution operation to the feature maps and uses a leaky ReLU activation function with a slope of 0.2. A zero padding 2D layer is added to pad the feature maps with an extra row and column of zeros. A batch normalization layer is added to normalize the activations of the previous layer. Another dropout layer is added to regularize the activations of the previous layer. Another CONV 2D layer is added with 128 filters, a kernel size of 3 by 3, and a stride of 2. This layer applies another convolution operation to the feature maps and uses a leaky ReLU activation function with a slope of 0.2. Another batch normalization layer is added to normalize the activations of the previous layer. Another dropout layer is added to regularize the activations of the previous layer. Another CONV2D layer is added with 256 filters, a kernel size of 3 by 3, and a stride of 1. This layer applies another convolution operation to the feature maps and uses a leaky ReLU activation function with a slope of 0.2. Another batch normalization layer is added to normalize the activations of the previous layer. Another dropout layer is added to regularize the activations of the previous layer. Finally, a flatten layer is added to flatten the output of the previous layer into a 1D vector. A dense layer with a single neuron and a sigmoid activation function is added to output a probability score that represents the likelihood that the input image is real. The function returns a Keras model object that takes as input an image and outputs a probability score. Overall, this code defines the architecture of the discriminator model and returns it as a Keras model object that can be compiled and trained on a dataset. A lot of changes have been made in GN's architecture since Goodflow's original paper, but some things remain the same. Normalizing the input. The activation function in all except the last layer of the generator must be a ReLU. The activation in the last layer of the generator, which is a dense layer, is 10 activation. Same goes for the discriminator. All the layers except the last have ReLU as active 10, and the last dense layer uses sigmoid activation. We use binary _cross entropy method to calculate loss in both the adversaries, though in some papers like Wasserstein-GAN, different loss functions is used. Now some hacks/tips that have been introduced in papers in the last few years to make GNs better are using batch normalization in all layers except the input layer in the generator and the output layer in the discriminator, using atom optimizer for the generator and SGD for the discriminator, adding some random noise to the labels before feeding them to the discriminator, sampling from a Gaussian distribution instead of a uniform distribution, construct different mini-batches for real and fake, i.e. each mini-batch needs to contain only all real images or all generated images. Pre-training the discriminator. Adding some noise to the images before feeding them to the discriminator. It's not necessary that all of the above tricks will work for your model. You will have to find the ones that do. This code builds and compiles a Generative Adversarial Network (GN) model using the discriminator and generator models defined earlier. The discriminator model is built and compiled first. It is compiled using the binary cross-entropy loss function, the atom optimizer with a learning rate of 0.0002 and a momentum of 0.5, and the accuracy metric. The generator model is then built using the build_generator function defined earlier. Next, a Keras input object, Z, is created with shape, latent_dim, which represents the input noise vector for the generator model. The generator model is then used to generate an image, IMG, by passing the input noise vector, Z, through the generator. The discriminator model is set to be not trainable, so that only the generator model is trained during the training process. The discriminator model is then used to determine the validity of the generated image, IMG, which is passed through the discriminator to obtain the probability score, valid. The discriminator is not updated during the training of the combined model. Finally, a new Keras model object, combined, is created with the input noise vector Z and the probability score, valid, as inputs, and the binary cross-entropy loss function and the atom optimizer with a learning rate of 0.0002 and a momentum of 0.5 as the loss function and optimizer, respectively. This model represents the entire GN model and is used to train the generator model to generate images that can fool the discriminator model. This code defines a function called show_ims that generates and displays a grid of 16 images generated by the generator model at a given epoch during the training process. The function takes an integer, epoch, as input, which represents the epoch number during the training process. This epoch number is used as a label for the plot of generated images. The function first creates a random noise vector with shape, r*(c), latent_dim, where r and c are both set to 4. This vector is used as input to the generator model to generate a batch of 16 images. The generated images are then rescaled from the range -1, 1 to the range 0, 1 using the formula gen_ims equals 0.5 asterisk gen_ims plus 0.5. A new matplotlib figure and axis objects are created to display the grid of generated images. The grid has R rows and C columns, and each axis object displays one generated image. The function then loops through each axis object and sets its image to one of the generated images using the inShow function. The axis function is used to turn off the axis ticks and labels for each image. The resulting grid of generated images is then displayed using the show function of the matplotlib.pyplot module. Overall, this function provides a way to visually inspect the quality of the generated images at different epochs during the training process of the GAN model. This code defines a function called show_losses that displays a plot of the discriminator and generator losses during the training process of a GAN model. The function takes a list of tuples, losses, as input, where each tuple contains the discriminator loss and generator loss for a single training epoch. The function first converts the list of tuples to a number py array using np.array losses. A new matplotlib figure and axis objects are created to display the plot of losses. Two lines are plotted on the same axis, one for the discriminator loss and one for the generator loss. The discriminator loss is plotted in blue, and the generator loss is plotted in orange. A title is added to the plot, and a legend is created to label the two lines. The resulting plot of losses is then displayed using the show function of the matplotlib.pyplot module. Overall, this function provides a way to monitor the training progress of a GAN model by visualizing the changes in discriminator and generator losses over time. Now we are going to train our model. This code trains the GAN model using the discriminator and generator models defined earlier. The training process is controlled by several hyperparameters. Epochs is set to 30,000. Batch_size is set to 32, and display_interval is set to 5,000. The input images are first normalized to the range -1, 1 using the formula x_train equals x_train / 127.5 to 1. Next, two number py arrays valid and fake are created with shape batch_size 1. These arrays are used as the ground truth labels for the discriminator model during training. The valid array contains all ones, while the fake array contains all zeros. The training process then begins with a loop that iterates over the specified number of epochs. For each epoch, the discriminator model is trained first. A random batch of real images, IMs, is selected from the training dataset, and a batch of noise vectors, noise, is generated using number py. The generator model is used to generate a batch of fake images, gen_ims, from the noise vectors. The discriminator model is then trained using these batches of real and fake images, and the resulting discriminator loss, d_loss, is calculated as the average of the losses for real and fake images. After the discriminator model is trained, the generator model is trained. The generator model is trained to generate images that can fool the discriminator model, so the ground truth labels for the generated images are set to all ones, valid. The generator loss, g_loss, is calculated based on the discriminator's response to the generated images. During training, the function also periodically prints the current epoch, discriminator loss, and generator loss, and displays a grid of generated images using the show_ims function. Overall, this code trains a GAN model to generate new images that are similar to the images in the SAFAR 10 dataset. The show_losses function is designed to display a plot of the discriminator and generator losses during the training process of a GAN model. To use this function, you need to pass it a list of tuples, losses, that contains the discriminator and generator losses for each epoch of training. This will display a plot of the discriminator and generator losses over the course of the training process. The x-axis represents the epoch number, and the y-axis represents the loss value. The blue line represents the discriminator loss, and the orange line represents the generator loss. Let's have a look at the original images. It will help us to compare how well our generator did. I have only selected the bird images for training. This code displays a grid of 40 images from the CIFAR10 dataset. The first line selects the first 40 images from the dataset and rescales them from the range -1, 1 to the range 0, 1 using the formula s equals 0.5 * s plus 0.5. The second line creates a new matplotlib figure and axis objects to display the grid of images. The grid has 5 rows and 8 columns, and each axis object displays one image. The third line uses a loop to iterate over the 40 selected images and set the image for each axis object using the imShow function. The axis function is used to turn off the axis ticks and labels for each image. The resulting grid of images is then displayed using the show function of the matplotlib.pyplot module. Overall, this code provides a way to visually inspect the images in the CIFAR10 dataset. This code generates a grid of 40 images using the generator model of the GAN. The first line creates a random noise vector with shape 40, latent_dim, using number_py. The second line generates a batch of 40 images using the generator model and the random noise vector. The generated images are rescaled from the range -1, 1 to the range 0, 1 using the formula generated_images equals 0.5 * generated_images plus 0.5. The third line creates a new matplotlib figure and axis objects to display the grid of generated images. The grid has 5 rows and 8 columns, and each axis object displays one generated image. The fourth line uses a loop to iterate over the 40 generated images and set the image for each axis object using the imShow function. The axis function is used to turn off the axis ticks and labels for each image. The resulting grid of generated images is then displayed using the show function of the matplotlib.pyplot module. Overall, this code provides a way to visually inspect the images generated by the GAN model. Since the model was trained to generate images similar to those in the CIFAR10 dataset, the generated images should resemble images of birds, which were the target class of the GAN model. Thanks for watching. Check the link in description, and I will see you in the next one.